Hi, welcome back. This is chapter 5, section 5.1, starting with exponent properties. So we're going to start by talking about exponents and what they are. And it's very closely tied into what multiplication is. If you remember, multiplication is just repeated addition. Instead of writing the same thing over and over and over again, here I have 2 plus 2 plus 2 plus 2 plus 2 plus 2, but really I can just say, well, there's 1, 2, 3, 4, 5, 6 2's. And that's what multiplication is. This is 2 6 times, or 2 times 6, right? So multiplication is just a notation that indicates this happens over and over and over again. And the same thing happens if multiplication happens over and over again. Let's say, for example, I have 3 multiplied by 3, multiplied by 3, multiplied by 3, multiplied by 3, however many times, it doesn't matter, right? There's a lot of them. But instead of writing this repeated multiplication over and over and over and over again, I can count up how many times there are a factor of 3. So 1, 2, 3, 4, 5, 6, 7, 8 of them. So I would write this as 3, and I indicate that there's 3 being multiplied 8 times with a superscript, an elevated or raised up number, and this would then be read as either 3 to the 8th power right? It's either read as 3 to the 8th power or simply as just 3 to the 8th, right? But that really means that I have 3 factors. Or sorry, I have 8 factors of 3 being multiplied together, right? So we can kind of go both ways with this notation. If I see something like, say, 4 to the 5th, and I'm asked to expand that, that means 4 multiplied by 4 multiplied by 4 multiplied by another one, and the 5th 4, right? It means 5 factors of 4. Right? 2 to the 3rd is 2 times 2 times 2. And this is our exponential notation. Right? All right. We can actually evaluate some of these things, like say if we're asked to evaluate, that means not only either expand it, but actually perform the multiplication as well. So evaluate. Let's say 2 to the 4th, right? I can think of this as 2 multiplied by 2 multiplied by 2 multiplied by 2. And if I just go step by step, 2 times 2 is 4. Then I still have multiplied by 2 multiplied by 2. 4 times 2 is 8. Still multiplied by this last 2. And then 8 times 2 is 16, right? So 2 to the 4th is 16. 3 to the 3rd is 3 multiplied by 3 multiplied by 3. 3 multiplied by 3 is 9, times that last 3 gives me 27. Right? And we're done. It's been evaluated. Now these numbers get pretty big pretty quick. Right? Let's take a look at a few of these. If I have, say, 4 squared, that's just 4 times 4, which is 16. That's not too bad, right? 4 to the 3rd is 4 times 4 times 4, which is 16 times another 4, so that gives me 64, right? A little bit bigger. 4 to the 4th is 4 times 4 times 4 times 4. That would be 64, because that's 4 times 4 times 4, just times another 4. Right? And that's 256. So that's a bigger jump there. And if I keep going, let's go 4 to the 5th. That's just 4, 2, 3, 4, 5 4s. But 4 4s was 256. Times 4 again is 1024. Right? And then if you see, we're going to skip 6. Let's just go straight to 7 here. 4 to the 7th is 4 times 4 times 4 times 4 times 4 times 4 times 4, but that is 16,384, right? It gets very large very quick, right? I just skipped one in between here. The next one is just 4,000 and some change, right? But they get big. They get large as our exponents get larger. Right? Okay. So we can play with exponents as also over x's. So if I have something like x to the third, and I multiply that by x to the fifth, right? I can think of this as x to the third is x times x times x, and then I'm just multiplying on x to the fifth, which is just x times 3, 4, 5 of them, right? This was x to the third. These guys all came from x to the fifth. But it's just a big list of things being multiplied again, so I can condense this down into exponential notation as x to the 1, 2, 3, 4, 5, 6, 7, 8 of them. But I just added 3 and 5 together, right? And so that's our first little rule, I guess, or little property, is that if I have x, some number or variable raised to 1 power and the same variable or number raised to a different power, I can say that it's that variable raised to the sum a plus b, right? So that is to say, if I have x to the fifth multiplied by x to the sixths, I can just say that this is x to the 5 plus 6, which is x to the 11th. I just add those together, right? And that's my first property. All right, let's look at this guy. If I have, let's say, x to the third, and I have that raised to the fourth, and what do I have here? Well, raising x to the third to the fourth means I'm taking x to the third times x to the third times x to the third times x to the third. There's four repetitions of x to the third, right? It's x to the third to the fourth, so there's 1, 2, 3, 4 of them. But each one of these follows that last rule. X to the third times x to the third is x to the 3 plus 3, which is 6, but then plus 3 more, and then plus 3 more, right? So I'm really just adding these. It's just x to the 3 plus 3 plus 3 plus 3. But you'll note that x to the 3 plus 3 plus 3 plus 3 is x to the 3 times 4, which is these two numbers. So I'm just multiplying these two. So if I have something raised to a power, and then that is raised to another power, it's the product of those two powers. And that is written this way. X raised to one power and then raised to another power is the same thing as simply x raised to a times b power. Now we can see that in action. If, let's say, it's not necessarily an x, let's say it's a 3 raised to the 5th, and then that's further raised to the 7th, right? Well, this is the same thing as 3 raised to the 5 times 7, so that's to the 35. Don't bother expanding this one out. If you have a calculator and you try, it'll give you something weird because this is a humongous number, right? So don't worry about that just yet. If I have, let's say, x times y, and that gets squared, or cubed, sorry. This is the same thing as taking x times y times x times y times x times y. So I'll write that as x times y gets multiplied by x times y, that gets multiplied by x times y, right? The multiplication is associative, which means it doesn't matter if I do x times y or x times y times x. but it's also commutative, so I can kind of shuffle stuff around. I can rearrange this. I can say instead of x times y in a group, I can just say this is just x times y times x times y times x times y. And I can reorder this and write all of my x's in front. And I can write all of my y's there, right? But x times x times x is x to the third. Y times y times y is just y to the third. And so we typically like to see this little shortcut here, that if I have the product inside a parentheses that gets raised to a power, each of those factors simply gets that power, right? And that would be written this way: x y to the a is equal to x to the a y to the a. I can see that in work here. Even if I have a number, say 2xy all squared, each one of these, including the 2 is a factor, so this becomes 2 squared times x squared times y squared, which I can evaluate 2 squared, that is a 4, so I have 4x squared y squared. Good. This also happens to work if instead of a product, I have a quotient. For example, if I have, say, x over y, and that all gets raised to, let's just say, the third, that's the same as taking that x over y and multiplying it by x over y and multiplying it by x over y. Excuse my funky x on the last one. But if I'm multiplying, this is just simply the same as taking x times x times x in a numerator and y times y times y in a denominator. But I can also write x times x times x as x to the third, y times y times y is y to the third, and so that same property appears here, that if I have a quotient that gets raised to a power, the numerator gets that power and the denominator gets that power. And we would write this way: x over y all raised to the a is the same as x to the a divided by y to the a. And so we can see a little bit more complicated problems arising from this. Let me get rid of this and show you an example. If I have something like, say, let's start easy. Let's say I have 3 over x, and that all gets raised to the third power, right? Well, then I can say the numerator gets raised to the third power, so 3 to the third, and the denominator gets raised to the third power. I can evaluate 3 to the third, so I will. That's 27 and over x to the third. Okay. Not too bad, pretty easy. Let's look at this one. Okay. I have 2x over y that gets raised to the fourth. To use that quotient property, that means that my numerator, which is 2x, gets raised to the fourth, and then my denominator, which is just y, gets raised to the fourth. But now I have the product property here, that product rule, that says I have a product being raised to the fourth power, and therefore everything inside that product gets raised to the fourth as well. And if you can evaluate one of these things, that 2 to the fourth, go ahead and do that. 2 to the fourth is 2, 4, 8, 16. So 16, x to the fourth, y to the fourth. Okay, good. All right. And as things get uglier, and they definitely will in this section, let's take a look at one big ugly thing here. If I have, let's say 3x squared y to the third over 4x, let's do a different one. Let's go w and z, w to the fourth and z to the second. And this whole thing gets raised to the third power. Right? If I want to simplify this, I can note that the denominator is going to get raised to the third, the numerator is going to get raised to the third. So working this out piece by piece, that numerator, 3x squared y to the third, gets raised to the third. As does the denominator, 4w to the fourth z squared also gets raised to the third. Right? Now I've got a product that gets raised to the third in my numerator. I've got a product that gets raised to the third in my denominator, so I will just distribute it, right? The 3 gets to the third, the x squared gets raised to the third. So this is 3 gets raised to the third. This x squared gets raised to the third, and this y to the third gets raised to the third. In the denominator, the same thing happens. The 4 gets raised to the third, this w to the fourth gets raised to the third, and this z squared gets raised to the third. Now I've got to use that multiplication property. X squared is being raised to the third, so this ends up being x to the 2 times 3, y to the 3 times 3, w to the 4 times 3, z to the 2 times 3, all of those. I can also evaluate 3 to the third. That's 3 times 3 times 3, which is 27. I can also evaluate 4 to the third, which is 4 times 4 times 4, which is 64. Right. X to the 2 times 3 gives me x to the 6. Y to the 3 times 3 gives me y to the 9. W to the 12. Z to the 6. And there it is. And I used quite a few of those properties all in one problem. Alright, good. What happens if I have, let's say, x to the 6th over x to the 3rd? If I write out x to the 6th, that means x times 2, 3, 4, 5, 6 of them over x to 3 of them, right? But these are factors that appear both in the numerator and the denominator, so a factor from the numerator will cancel a factor in the denominator, and again, right? And when I recollect everything, I have x to the 3rd. Since everything in the denominator canceled out, I'm dividing here, so if it all divides out, it's over 1. But I don't need to write that it's over 1, I can just write that as x to the 3rd. Right? But you'll notice what I'm doing here is essentially subtracting x's from the top as long as I have one to match from the bottom. And that is 6 minus 3 gave me 3. That's how this one works, is simply with that subtraction. And we would write that as x to the a over x to the b is x to the a minus b, because however many x's there are down here, I simply subtract that from however many were in the numerator. Right? Okay. So let's take a look at an example of this. Let's say I have, well, let's just go x to the, 25 divided by x to the 10, right? Instead of writing out x times x times x times x, 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 x over a whole bunch more x's, I can simply do that subtraction. This is x to the 25 minus 10, and so I get x to the 15, and I'm done. That's it, right? What happens if I end up with something like, say, x to the 5 over x to the 10? If I draw it out as x times 2, 3, 4, 5 of them in the numerator, and I now wish I didn't write 10 for the ones in my denominator, but here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them, right? If I start trying to slash these, one from the numerator kills one from the denominator, but my numerator runs out first, right? And so I can write this, since everything canceled out of the numerator, I have 1 and I have 5 left over in the denominator, right? And so this is 1 over x to the 5th. It is by definition by canceling these out, right? But if instead of writing them out, I use that same property, and I say, well, this is just x to the 5 minus 10, what happens here? I can call this x to the negative 5, and that's just another notation for saying that it's 1 over x to the 5th. And so if I have a negative exponent, that simply means put it down in the denominator, you can change it positive, right? So for our purposes, we have this definition. X to the negative anything, whatever that is the same as 1 over x to the that anything positive, right? And likewise, if I have a negative exponent in the denominator, I can pull that up to the numerator and change it to be a positive, right? So this is how we deal with negative exponents if they arise. If it's just x to the negative something, put it in the denominator, but if it's 1 over x to that negative something, pull it back up in the numerator and you can change it to be positive. Which leads us to something interesting, I think. If I just have x to the 1, that's just x, right? There's one factor of x, we don't bother writing it. It would be like saying we have 1 times x to the 1 divided by 1. All those 1's don't do anything, so we just have x, right? X to the 2nd is just x times x and so on. X to the 3rd, x times x, right? And that goes on forever, right? And if I have x to the negative 1, we just said that that would be 1 over x. And x to the negative 2 would just be 1 over x squared, right? What if you really want is the same as 1 over x times x. I think that's too high, probably. It is, yeah. So let me rewrite this. Did that make it in? Barely. Alright. So if I notice there's something missing in between negative 1 and 1, there's x to the 0, right? So the question is what does x to the 0 mean? I'm going to erase this because it's getting a little crowded and not beautiful. And I'm going to start over with, say, x to the 3rd. It's just x times x times x, right? X squared is just x times x. X to the 1 is just an x. And then what is x to the 0? And a lot of people say 0. That's wrong. It's not. Because if you look at the relationship between each of these, x squared is this x to the 3rd that I've divided an x out of. That 3 minus 1 gives me x squared, so that's x times x. And if I take this x squared and I divide it by an x again, that gives me just 1x. And so this guy, to follow this rule, would have to take the previous guy, x, and simply divide out an x. And anything divided by itself is 1. So anything to the 0 is 1, except for one little itty bitty thing. So let's say a to the 0 is equal to 1 unless. And that one unless is unless a is 0 itself, because 0 to the 0 is undefined. Because to get there, I would have to have divided by a 0, and I can't. So anything to the 0 is 1, except for that 0 itself. Okay, good. All right, now Let's look at one last thing here. If I have these negative exponents, I can play with them a little bit. If I have something like, say, x to the negative 2, y to the 3, over w to the second z to the negative 4. And I'm asked to simplify this and only write it with positive exponents. All I have to do is take the ones that are negative, that's the x and the z, and switch their places. X is going to go down, the z is going to come up, the y will stay where it's at, the z comes up to be next to the y, the x goes downstairs, I change its power to be a positive 2, and then the w stays where it's at. I get that. And that wraps up this section. I will see you guys next time. Take care.